it's something that is very close to my heart, something I've been working on for like now 4 years at Balena of how we actually do builds, tests, deploys of hundreds of operating systems for Balena OS. And this is going to be our talk, and we are taking a journey from PR to production on how we are able to achieve that through GitHub Actions and how we migrated from Jenkins, which was our last CI/CD. We'll start off with who am I? I am a product owner and documentation lead at Balena. We work at the hardware in the loop team and trying to build like an open source HITL application so that people can actually run their tests directly on devices, and I do documentation as well at Balena. I also run a documentation initiative to write technical documentation for startups, and that has been going well. It's called Mixter. Other cases, I'm very much involved in open source, and something you know about Balena is Etcher, and I'm very much involved in PyCon India, Alias, and Gen AI meetups in New Delhi, NCR. The special pronunciation for my name is Vipul, and we'll be pulling together quite a bit of concepts at 3 p.m. right here so that it not gets boring. And it's a really interesting journey on how we do testing, how we do embedded operating systems, and all that. So we'll start off with what's our subject, and that's Balena OS. Balena OS is an open source Yocto-based embedded distribution meant to run containers. Our entire thing is running containers on IoT devices. And it's fault tolerant, it's field tested, it's completely free, it's available for you to download, and it supports over 100 plus IoT boards right now. And the thing that comes across in this conversation is, haven't heard of it, right? But that's the most cases about IoT. IoT is so much all around us that we were the first ones to deploy Docker containers in space. You have in smart dustbins, CO2 sensors, farms, underwater drones, Dyson backpacks recently, and air water drones as well. And that's the magic about it. If IoT is in the news, something has gone wrong. It's making waves and making impact sort of like on the core infrastructure of a city, of your college, everywhere, silently. And there comes the stakes, there comes the problem. With your smart cities and your toaster even getting firmware updates, the challenges are huge. While software testing is already hard enough, testing software on hardware is downright painful. You have to worry about environment, you have to worry about a lot of different factors playing with your memory, environment, security as well for the hardware, wherever you deploy. And when things fail in production, they are actually real, and someone does get fired. So how do we see how, when we deploy software, it's actually tested on the device? And when environment factors like this happens, when someone parks their ship wrong, your company doesn't shut down. That's something we want to be fault tolerant against and anti-fragile. And that's the sort of challenges that you have when building a product around embedded operating systems or when your product is an embedded operating system. Fault tolerance, deploying release confidently, all of these things we have heard quite a bit in IoT. Coming to the starting. So what is the solution to getting software fault tolerant? And our solution was, how do we automate testing on the hardware? And that starts with just the two simple components that is always there in a test, a testing environment and a test thing that needs to be tested. So you have a controller that provides a testing environment sort of for the device under test, which is the Raspberry Pi 4 right here. And we have a situation where a lot of the times you have to test like if the GPIO is working, if the lights are coming on, if the HDMI is working. For my signage application, how do you exactly test that? How do you go forwards? Replace your fingers to plug in that SD card, plug out that SD card, and that's where AutoKit comes into picture. It takes over your testing environment, which is your device under test, and controls it fully. That's what the AutoKit is. That's how we enabled a hardware in the loop testing pipeline right here at Balena. AutoKit has like several features. It can flash on an SD card. It can control the power. It can turn the DUT on and off. Like the list is huge. But the thing that I really like to mention is it's completely open. So the STF files are available for download. So you can actually build this at your home right now. There is no custom hardware involved. All of it is off-the-shelf components. There are docs to build the AutoKit as well. So if someone has any complaints, you can tell me. I wrote them. And then it's free and open source. So we want everyone to sort of get into testing their software on hardware, and this is not something that we want to do it alone. And this is how it looks like. It's pretty jank, and we love it for it because you have a situation where on the top right, For my direction, that is true. In the top right, you have the host, where it's the one that is the controlling. And on the top, in the bottom left, you can see the DUT, which is an Intel NUC right here, which we use to control the device. And on the top, you can see an SD mux, which is used to flash the Intel NUC anytime we want. So if you want to change OS images, or you want to stress test how fast you can change OS images, or can you install a corrupted OS image, and what happens. You can see this in the sort of way that you are now replacing your fingers. You don't have to, you just have to write code to send signals to your AutoCAD to control your device. And that is how the CI/CD pipeline starts in an AutoCAD scenario. You can control power, you can capture HDMI, you can provide your own internet as well if you wanted 2G or 3G. And that is something that the AutoCAD really enables. And this is the sort of like pipeline that we have for AutoCAD, where your GitHub action or your GitLab CI/CD pipelines, whatever you use, nothing is in terms of competition. But whatever you want to use, you can just send signals that, hey, I want to do this to the device. The AutoCAD will say, yeah, sure, let's go for that. We'll turn on the device, run a few commands, and give you back the feedback. And that is hardware in the loop. This is what, when hardware is in the loop, you're getting feedback directly from the hardware. And that is something that is pretty cool. So let's talk about YAML. If we are talking about GitHub Actions, let's talk about our Lord and Savior, YAML. And this is where we start the journey for PR to production and see what happens. And it all revolves around this huge, big YAML file that we wrote, which I won't be going through all 1,233 lines of. But I've put on a link where people can actually check it out, see what it does with Yocto to build, test, and deploy. But we are going to talk about it right now. It all starts with a pull request. I think that could be a good motto for GitHub. But it all starts right here in our own repository, which is we are making a pull request in Balena Intel. And with Balena or with Balena OS, what happens is every time you have a device, it comes under a single repository. So Balena Intel creates generic AMD64. It creates a bunch of devices. So when someone like Ryan opens a PR at Balena OS, it will have builds started for it immediately in our GitHub Actions. And that is generic x86, generic AMD64, and Intel NUC. Intel NUC is the actual device type here, so let's focus on that. Drill down a little more how that looks like on paper. And yes, the builds do take a lot of time because you are building it on maybe not that much hardware, or you are trying to conserve. But something that is very good with Yocto distributions is you can cache a lot of them. So while you could expect that it would take hours, it actually takes like 10 minutes or so. And we build every single time. Every time someone commits, every time someone synchronizes, there is a new Balena OS releases being created, and then all those releases getting tested. You can see one of those tests failed. So these are sort of some of the triggers that we have for building, and then on PR open, PR close, and then dispatch. And this is how the caller workflow looks like for one of the device types. So the big caller workflow that I showed to you in the earlier slides is what we are calling upon, and that is basically how we do our testing. You have a caller workflow that calls on a composite, and you can decide triggers, you can decide execution parameters, you can have a lot of more control by using this sort of GitHub action workflow. Coming to next, now you have a freshly baked Balena OS. When your build stage is complete, you have the artifacts right here. What we also do is we upload the GitHub artifacts into the GitHub artifact storage. And that helps us to pass along these artifacts to the test stage. And you can see the storage and then the UI really helps to see, like, OK, what come out of this build, Yocto build when it happened. So you can figure out that thing very easily. Coming to next, this is sort of our current Jenkins look like. So this is sort of a scale review of where we are going towards with GitHub Actions. This happens per pull request, per commit. We build them all to try to see like how our Yocto build is not failing. So let's say I pushed a commit and that fails Yocto commit. That's something that we don't find acceptable. And we want to make sure the system is fault tolerant. So we build every single distribution. And it takes about 20 to 25 minutes with the cache. Once things get done, Leviathan takes over, which is our software testing suite, which connects Balena OS testing with the Intel NUC device that is connected to our AutoCAD. So you have a situation where now you need to do multiple things in the between, and that is the glue, that is Leviathan. So you need to find an available AutoCAD, you need to configure your Balena OS images, flash that OS image onto the AutoCAD. The same test suite needs to run for over 50 plus device types, so you need to sort of understand the complexity we are going through, where an example is Leviathan will sort of understand how to exactly flash a Raspberry Pi 3, a Intel NUC, a Jetson, a BeagleBone. And that's where, using that with GitHub Actions creates this reusable workflow that we don't have to manage quite a bit. And yes, it's free and open source as well. Once this thing is done, I know engineers would love this in the crowd. This is sort of how easy a test looks with Leviathan. You turn the worker off, flash, and on, and this is how it triggers the sort of release process, and you can sort of write automation steps with that. With the thing where we can flash and now issue some commands like, hey, can you run this disk image that I have? Can you run this Docker container that I'm giving you? And that is why Leviathan sort of helps glue it all together. And this is where the money shot comes in when we have our entire hardware in the loop testing setup. So this image is 2 years old, and this is the rig that we have in Athens. Every one of the AutoKits are now connected to a device that we are testing on. So once these can be thought of as servers that you give commands to, and you tell them that here's the inputs, here's the test them for me, and they give you feedback. That's exactly it for our case. And that is what hardware in the loop testing is. The workers automate provisioning, testing, and then giving you back the results from all of these AutoKits and give you back all the failures as well. So you don't have to exactly worry about like what happened when my OS image got corrupted, or what happened when the software that I had was a semicolon missing. You will get to know about it. You don't have to go into your hardware, and you don't have to use your fingers. That is the important part. And my God, we do so much testing with Balena and GitHub Actions, and that is something that we try to do more and more of, where we are running over 200 plus assertions over 62 tests, and that's why it takes so much time, over about 190 minutes to 120 minutes, where we are running assertions on like a managed cloud instance. Then we try to do it on unmanaged Balena OS release suites, and something of my favorite is break the OS purposefully to see if it can recover. Because for IoT devices, this is something that is extremely critical. Can they self-recover in the field so someone doesn't have to send a camel into the Sahara Desert to change an SD card? That is something that doesn't make sense for the business prospect, and that is something that we intentionally test. Can the OS recover in the time of power failure, memory card corruption, RAM issues, everything? And that's why we intentionally break things, and the AutoKit can easily recover that device right there. And that is something that the AutoKit really helps us power through. So once all your testing is done, once all your build is done, you come back, actions report back the results. And if you're lucky, then it says, like, everything is passed, right? There are so many variables at play, everything is passed. And if you're one of those lucky ones, then you probably also get reservations at Naru, because I didn't get one. But if you are getting that, good for you. That means now you have end-to-end tested your Balena OS release, and your operating system is actually tested on a device. Who can say that? Who can release? We can release as fast as possible, but this is about releasing as confidently as possible. Once it's done, once the approving checks or the required checks were completed, we get an approving review on the PR, and the PR is merged. This is something specific to Balena. As the PR gets merged, we trust our test that much, and this is years of pain later. As the PR gets merged, the PR gets deployed. We send it through the closed PR event on GitHub Actions. The action runs, deploys the PR directly to S3, and the API will give you near instantaneous new releases of Balena OS right here on our webpage. And you can check it out right now. The releases constantly update day to day. So every time there is a new update, we want to remain on the bleeding edge of all the firmware, all the updates that are going through. So we never had that issue when XZ, sort of the issue happened. We were always on the bleeding edge, and people can download the latest version of Balena OS. They don't have to wait for a release cycle. That makes your deployments really frictionless, and you can really jumpstart from the competition, get a jumpstart from the competition, and get ahead. Once you merge and deploy, this is something that we have for scale. Balena OS has 95 supported device types. 47 of them are supported on the AutoKit. Every device type has, like, for every PR, every commit, you do a new Balena OS release. Every Balena OS release gets through 3 rounds of test suites, which is OS, Cloud, and Hub, and we test them daily. So these releases are all in the ballpark, but I can tell you, like, once it's fully deployed on GitHub Actions, we'll easily cover this. And that requires cost savings, optimizing, and that's something that GitHub Actions really well provides, and we'll talk about it more, of how Balena OS is doing CI/CD at scale. For, like, giving a good summary, I've included a very nice diagram here, where we start from the top, when the PR opens, from GitHub pull request to a Yocto build, uploading the artifacts, Leviathan test, and then it comes back around. If the test merged, then the PR merges, and then you can come down where once we declare a tagged version, that's when a PR is complete, and the builds get successful and sent to S3. Sometimes we also do, this is not as simple as just saying Balena OS, we also do secure boot images, We also do ESRs, and we also do AMI releases for S3. So there's a lot of artifacts get created from every single release. So this is something that we have worked out, and this is not something that really came about like last night or 3 months ago. Years has been gone into it. And that's something that we are presenting to the community now as an open source measure, that you can actually get started with your own hardware in the loop testing. So what did we, in fact, use in the GitHub action? A lot of the features that you already know and love are already there, but something that really helps power through the GitHub actions has been the community participation. So Jenkins and other CI/CD platforms, while they are very good, they are also logged in behind a sign-in wall. So your community members or your partners or your customers can't actually see what's going on with your build. Why is the build failing? And that's what GitHub actions give back to you. A lot of good logging, a lot of good UI explanation tips, context retrieval, transparent logs, and the ability to have, I think, 90 days, if I'm not wrong, for a log rotation period is very nice. And that way, GitHub helps quite well in terms of its competitors. And you can really see, like, if something really breaks down in an OS later, we can see if the test failed or not. And then we can go back, improve our tests. So it's all a feedback loop that you can complete with the customers. Moving on, you can bring your own runners. Does help that this exists. You can get started immediately using GitHub's self-hosted runners, or you can buy one if you're on the enterprise plan. And this is like one of the examples of the large hosted runners that you can get. Or it's BYOR, which is bring your own runners. And there are many more services that are coming, something like Actuated or CI Run, that you can lease AWS S3 or EC2 servers and then make them into GitHub Action servers, GitHub Action runners, and that thing can bring a lot of cost savings. So there are options. There is flexibility to go up and scale Balena as well, but also your own GitHub Action pipeline, and make it quicker as well if you are not doing cross-architecture compilation. The last thing that is my favorite is you can maintain environments. So environments are readily available and readily maintainable right in your PR workflow. So you can check which environment got used, is it staging being deployed on, which secrets were used, and that gives you a clarity that is something that I've not seen anywhere else, and that sort of helps quite a bit to make the right decisions. Coming back, this is something of my favorite section. How do I use this at work? Because the talk is all fine, but I love a practical use case. How do I use this today at work? So a simple use case that I love to show people is you can use the AutoKit to manage devices that can't be managed. Sometimes you have Apple Mac Minis running at your home. Some people are into app development, and they have Apple Mac Minis at their home office or sort of like in the work. So you can have an AutoKit connected to each of them and power them off, flash new firmware, update them in after hours. No one has to wait around for it, and that's where AutoKit comes up as like a controller or a worker that can make sure all the changes get through. Then if you are into building cross-architecture applications, then AutoKit is like great. You can target the exact device for it that you're building it for, or ARM v7, ARM v8, and then you can connect an AutoKit to it, test every build of your software on the hardware directly. And that's where your team can get the confidence and the sort of improvement in their workflow that it really helps to give back the right feedback. So you can actually see like what's happening with their builds, right? Everyone loves that. And you can get feedback on the changes right in the PR, and the PR can get fixed. So no one is pushing broken ARM v8 builds. No one likes that. The last thing is quality assurance and stress testing, where you can have this on a factory floor setting, and you can sort of run through like a lot of the quality assurance tests, put it through stress testing, see if it can work in an environment where you can't emulate, but the AutoKit can because of the reality that it works in. And something that QEMU can't do is this sort of function right here, where you can actually go out and test quite a bit of hardware. And yes, you can test operating systems too. And that's the talk. But coming down, what we learned is testing operating systems in the field is very important. Surely it's painful to scale. Like it took a couple of times, a couple of tries to figure it out. Even with software, it would, right? But the pain doesn't have to be, and it's really beneficial when you're testing on the hardware and with GitHub Actions. These are some resources that I've used in the slides. And thank you. That's about it.